All right, welcome everyone. My name is Dean Wampler. This is a talk about why Scala has conquered the big data world. Why is it that it's such a good language for this domain, I guess you'd say, and how it got there. I'd also like to recommend that you check out Vitaly Gordon's talk from yesterday. Of course, obviously it's past, but you'll be able to get the video and slides soon. And there were two talks yesterday on Spark. Vitaly in particular, he's got an interesting story because he basically runs a data science group at Facebook and realized pretty early on that he really needed to be writing code in Scala, even though he came from a background where maybe Python or R was more traditional. Most of the photos in this presentation are from the North Cascades National Park in Washington, where some of the typesafers grew up. But actually the next slide isn't. It's from the Bay here in San Francisco. And you know, San Francisco was a very health-conscious place, right? There's this world-famous Greens restaurant just a few blocks or a few feet away. Lots of yoga studios, great coffee and all that. But I really didn't understand how serious they were about being health conscious until I saw this ship while I was crossing the Golden Gate Bridge this past Sunday. They actually have a ship named No Smoking. So that's how serious they are. I've written some books. Actually, the reason this slide here isn't to sell the books, although they are available at a very reasonable price. It's actually because I believe every developer talk should have some XML, so there you go. So I started doing big data consulting in 2011. I wanted to get into this space. I worked for a consulting company that mostly focused on Hadoop, and I got pretty frustrated really quickly with the developer experience. It was a nasty set of tools, very unproductive. Very frustrating. So basically my LinkedIn profile looked like this, or should have, about that time, because I sort of started trolling the Hadoop community. In particular, at the Northeast Scala Symposium in Boston, almost exactly 3 years ago, I did a talk, why big data needs to be functional. Why are we using this old style Java coding when we could be using something that fits much better? This picture is actually from Wyoming, it turns out. And I made this claim that Hadoop is the enterprise Java beans of our time, because for me it just sort of took me back to the bad old days of an attempt to do enterprise Java that actually failed because it was all completely wrong. But we learned from that experience and came up with better ideas. And I think that's the stage we're at right now with big data systems like Hadoop. So let's go back on a little trip on memory lane a little bit and talk about Hadoop and where we were then and how we got to where we are now. So Hadoop really started to get mainstream attention around the 2008 timeframe, and one of the driving factors was this blog post from Yahoo, who had been nurturing Hadoop for a while. And this is posted, September 2008. They said they have a node, 4,000 nodes of Hadoop running in their environment, 16 petabytes of data. And actually those numbers are kind of quaint by today's standards. Today you would be excited if you heard about a cluster that was 10 times as big. Maybe the date hasn't multiplied by 10, but that's, anyway. So that's how we got from there to here, which isn't that long ago actually. So just for context, what is Hadoop cluster? Well, typically it starts with a few master nodes, a whole bunch of slave nodes. The slave nodes have massive numbers of hard drives that are holding all the data. There's this virtualized file system called the Hadoop Distributed File System. It's managed by this name node service, and then the data nodes know where all the blocks are buried in the hard drives. And when you write your Mapreduce jobs, you would submit them to this what's now called a resource manager in current versions, and it would figure out how to split up your job into tasks, which are individual JVM processes that would run on each of these slave nodes. Usually try to be close to the data so you don't move as much data over the network as possible. So that compute engine, as opposed to the storage, was called Mapreduce, and that was what we wrote everything in those days. And just to make this concrete, I'm going to work through an example today in several iterations called the inverted index. And this is one step up from the classic hello world, which is word count. This is a little bit more interesting, which is why I'm talking about it, but it's not that hard to understand. And it's the basis of search engines, like what Elasticsearch does, what Google Search is doing. Imagine that I've got these web crawlers that they're constantly all day long crawling the interwebs, and let's say they're hitting Wikipedia right now, and they find these various pages for Hadoop projects like Hadoop, HBase, which is a database in Hadoop. Hive is off the screen. That's a SQL query tool. And then what it's going to do is build up this simple data set, 2 columns effectively. That could be stored in files, though, whatever. The first column, sorry, I'm jumping ahead. This is what we're going to end up with. We want to know which of all these documents mention Hadoop, which ones mention HBase, and so forth. So we're going to end up with a 2-column output that will be indexed by words, and then we'll have these tuples, a list of them, as the second column, which will be, where was this word found and how many times did it appear at that location. For my trivial example, the counts are always 1, which is a screw up on my part. So anyway, in a more realistic world, it works in a 2-stage process. As I started to say, I've got web crawlers that are crawling the interwebs. They're building up this intermediate data set here, which I'll talk about in a second. Then some sort of miracle is going to happen to end up with the final result that we just went through. So this intermediate data set is also basically a 2-column table, if you will. And I have this block delimiter because typically you write things in huge blocks on files in HDFS, like 64 megabytes, 128, some multiple like that, because you want to be able to scan data off hard drives contiguously and write it contiguously, because hard drives circa 2004 were all made of spinning rust, and that was slow to access if you had to move the heads around, and et cetera. Anyway, we're going to basically walk through this, the internet, and we're going to write this data structure where the first element will be the some sort of ID for where I found this document, and I'm just going to use the URL or some simplified version for now. And then the entire contents of that page will be the second column. Maybe cleaned up in some way, but that's not really important. All right, so let's go back to this second part. So we already talked about this. I'll end up with data something like this. Let's look at the HDFS line. That's the most interesting. Of my trivial input data set, I'm going to have 3 places where HDFS was found, 1 occurrence on each of those pages. All right, what's the miracle here? Well, it turns out you can actually implement this with a single Mapreduce job. That's where the name comes from. There's this big chunky step called map. There's another chunky step called reduce. And there's this magic in the middle called sort and shuffle. I have to write the map task. I have to write the reduce task. Everything else is done for me, the sort shuffle. So what's going to happen is I'm going to spin up individual map tasks. These are the JVM processes for each of those file blocks that I mentioned. And what each map task is going to do is read in one of those records, one at a time. It's going to tokenize that document effectively, and then spit out a bunch of new tuples, which will be each word it found, and then some nested tuple. Although it doesn't have to really be nested, but just to make it fancy, that'll be like the original document ID and the count for that word in that document. So this is what's coming out of the map tasks. Fairly straightforward. It's actually pretty easy, at least conceptually, to describe this. It's nasty as hell, as usual, to write this. So what the sort shuffle process does is it first sorts all of those records by key in each map task locally, and then it shuffles those key value pairs over the cluster network. And what I want is, say, all of the H's, all the keys that start with H, to show up at the first reduce task. Including all of the Hadoops, all of the HDFSs, and so forth. And then I'm going to aggregate together all of those key value pairs with the same key. So the input to the reduce step is going to look something like this. Either I have to write code like this, or maybe the infrastructure can actually do this step for me. But basically it'll be like 1 occurrence of Hadoop, and then some iterator that goes through all these key value pairs that came in over the network. And then the final step is just to format that result however you want it, so that I have a single entry for the word Hadoop, and then all of the occurrences of that word, wherever it occurred anyway. Okay, so hopefully you followed that. That's not a terribly complicated algorithm to follow. A lot of these big data algorithms are something like this, where you stage transformations with key value pairs and so forth. So what's not to like? Well, the first problem is that it's actually hard to implement non-trivial algorithms. If you have to stage several of these MapReduce jobs to get the job done, it can be a somewhat advanced exercise to figure out how to do it. My favorite example of this is secondary sort. So if you're used to writing SQL, you might say something like, order by name ascending, age descending, or something like that. A trivial thing to write. It is unbelievably complicated to actually implement this in MapReduce. It's sort of a test of your expertise in the API to just write that very simple kind of thing. Which gets to the second point, which is the MapReduce API is really horrible. So I'm going to take a chance, and I'm going to show you some Java code. If you're offended by Java, please avert your gaze. And I won't go through this in detail, but I just want to make some general points. So for color coding, I'm using this sort of blue color for types. Oops, looks like I'm using it for keywords too, maybe. Well, some of them, like void. But what I really care about is the red, like the name here. Because the red, those are all functions or methods. Those are what do the real work. All this object stuff is ceremony to help us manage complexity. But what we really care about is getting from point A to point B, and those are what methods do. So what I really care about are the methods. So if you look at most of them in the main routine, you might say, gosh, there's a lot of methods there. This is good, right? Well, no, it's not good because I'm just setting properties. This is like, it's not really carrying much weight, all of this boilerplate that hopefully the system, you would think, could figure out for me, but it can't. So there's a lot of ways I can make mistakes without getting much done, even if I get it right. So that isn't good. This is the end of the main routine where once I finish all of the sacrificing chickens and that sort of thing, then I start my job running and let it run. This is the actual class that does the mapping. Yeah, it's a nested class. And once again, lots of ceremony. This is Java, so I've got lots of type, spew. And I have to do crazy crap like I can't just use strings and longs. I have to use this custom wrapper serializable type in the API, which is the thing that really reminded me of the EGB API. How many of you actually lived through that? Anybody want to admit to? Okay, I can see the pain in your eyes. Well, it's kind of the same sort of experience here. But anyway, this bit here is really actually the bit that I went through on the diagram of actually tokenizing and spewing out new key value pairs. And even that's complicated looking because it's Java. But I had to go through all this stuff just to get here. And I'm still not done. I still have to do the reduction step, more type spew. And then finally down here, I'm actually iterating through values to build up the final result. So a relatively simple algorithm, but just a whole lot of ceremony. And actually, I lied to you a little bit, although I'm kind of blocking it here for those of you on your right. I didn't actually do the counts. I said I wanted to count how many times words occur, because obviously in a search index, I don't want to know who just happens to mention Hadoop in passing. When I search for the word Hadoop, I want to know about the documents that are obsessive about it, that are talking about it, constantly. But I didn't even calculate that part, because basically by the time I got here, I'd sort of lost the will to live, let's be honest, and I didn't want to keep going. So here it is all together, and I can't even read this with this glare, but this is 6-point font for those of you in the back, the whole thing together. All right, so what can we say about this? This is a mine, a wrecked mine in the Olympic National Park. No connection at all to what I'm talking about. But anyway, you basically get lost in all these trivial details, and the things that you really care about, like tokenization and manipulating tuples, you have to do all that yourself. So it kind of sucks. So at 2011, 2012, it seemed a little daunting. We had this huge objective. The little guys down here trying to get up there, and so what are we going to do? Well, actually, there was already hope on the horizon at that point. Twitter, had this problem in spades, and they needed a solution, and they didn't want to keep writing stuff like this. They were using an alternative specialized language called Pig that just wasn't meeting their needs. By the way, there's 2 deer right here on the snowfield, and they're about to reach the pass, so they're going on for new horizons or something. I'm not sure what they were up to. But nevertheless, what Scalding was, that Twitter wrote, was a Scala API for writing big data applications on top of MapReduce. And to be clear, it's actually based on a really nice Java API called Cascading that gives you a lot of the data flow abstractions that we would want when we're trying to think about data problems. but still has a fair amount of ceremony because it was pre-Java 8 Java. And all that is sitting on top of Mapreduce. So here's the same program I just wrote in the Scalding API, and just quickly, I put it on 2 slides just so that it would be readable, but it's so much smaller. It's, it's less than half the size. Without going into a lot of detail, notice they're using Scala Symbols. How many of you knew that a tick mark followed by a word was a Scala symbol? Yeah, you don't see those very often. They're using those to reference fields by name. So this is their so-called field API. But basically, if I said red was good, so look at this. We've got flat map. That's our old friend. That's what we're using for tokenizing a string into words. So it's actually, when I read in a line from that original record, I'm not just mapping, I'm flat mapping, right? Because I have one input record, I might have 0 to many output words. So in fact, it really ought to be flat Mapreduce that we've been using all this time. But anyway, to be pedantic. Split and map, these are our friends. What we're doing here at the end is outputting words and then whatever ID we were using to reference the document. And then the last bit, so that's like the map task that we described. And then look at this, group by. If you've ever written a SQL query, you've probably written group by, and that's the logical thing to use when you're trying to get together records by some key. When you want to get together everything that has the same key, in this case the word. So I'm just doing a group by and then converting it to a string and then writing out the result. So most of the ceremony just disappeared. I focused entirely on the problem domain. I turned what was a software engineering hassle into writing a script. A lot of it used to be scripting languages. That was like a pejorative, right? Oh, he's using a scripting language. But I believe that everything we write should actually be a script, basically. If I can get it that small, chances are it's right when I first write it. There's 2 different kinds of right in there. And it's going to work, and even if it doesn't, I can fix it quickly. So I'm not really interested in writing big software projects anymore. I want to write small stuff like this. Well, we still have problems. So this fixed the problem of I almost used a bad word there, of a bad API that we don't want to use anymore. But we still have this issue, still we have other issues with Mapreduce. And one of them is that increasingly we don't want to wait for data to come into our environment, sit on the hard drives, and then maybe 2 or 3 hours later we'll kick off this big batch job to process it. We'd actually like to get that information out of the raw data much more quickly. It becomes a competitive advantage. So the fact that Mapreduce is completely batch mode oriented is actually another drawback that we need to solve. And in fact, a solution was developed for this of handling event streams, and that solution was Storm, that was invented by Nathan Marsh. Now this isn't a Scala project, it was actually written in Clojure, and it was part of the so-called Lambda architecture, the idea that you might have a batch layer that's processing all the historical data and writing it to some fast lookup service like a database. You don't want to just run this big batch job to get it answered quickly. But then when data comes in, I'm also going to process it with a so-called speed layer. And then my queries have to be able to query both layers. Well, there's actually a couple of problems with this model, and that's why I think the Lambda architecture is a transitional model to address problems we had, circa 2012 and so forth. Namely, that it becomes very difficult to actually avoid duplicating the same logic in both of the top and the bottom. And my query engine also has to be able to query 2 things all the time instead of 1. So it's not a perfect model, but it did get us around this initial problem of being able to still use Mapreduce but handle event streams. So in fact, Twitter tried to solve this too, at least the duplication problem, by coming up with an API called Summingbird that sat on top of Storm and Scalding. And they would say that they had mixed success with this, that it wasn't it helped, but it wasn't a perfect solution. Another problem with Mapreduce is that it's extremely inefficient. If you have to sequence multiple Mapreduce jobs together, it turns out that Mapreduce has no idea of the overall data flow, so the only thing it can do is flush all that intermediate data to disk and then reread it back in at the next job. And that can be a huge performance loss. So you'd really like something that's smart about the entire data flow and knows what to cache in memory and what to throw away, that sort of thing. And yeah, we'd still like a system that maybe makes it easier for us to do both batch mode and streaming with maybe 1 tool or at least a minimum number of tools. And it turns out the reason everyone is excited about Spark, which you may have heard of, and if you're in the big data world, I know you've heard about this. I was at Strata down in San Jose a few weeks ago, and even though it's Strata plus Hadoop world, it was really Spark plus Strata plus other things, but it was mostly a Spark conference. Why is this great? Well, we're going to look at an example, but what does it address the problems I mentioned? Well, it actually has a wonderfully elegant and concise API, very similar to the Scalding API we saw. And the key thing is it's based on functional programming, and I'll come back to that point in a little bit. It's also very flexible for different kinds of algorithms that we might need to implement. MapReduce is terrible if you need to implement something that's highly iterative, like training a machine learning model or traversing a graph, whereas Spark is lightweight enough that you can actually do those with reasonable performance. I mentioned this a second ago. It actually keeps this data flow directed acyclic graph in memory, and so it knows what to cache and what not to cache for intermediate data. It also does things like, you can write things like, say, a sequence of map, flat map, filter, those kinds of operations that I can easily pipeline together into one JVM process. It does that kind of stuff, which is really valuable too. That's what I mean by combined steps. Because Spark is actually very efficient for the most part, even though it was actually also implemented as a batch mode tool originally, they realized that they could actually process very tiny batches. So the way they address streaming is with a mini batch model where you basically capture windows of events like down to a second or so resolution, and then you process them with the same infrastructure that you would use for a batch job. And that's what gives us code reuse across streaming and batch mode. In fact, usually when you look at a streaming job versus a batch job, there's different setup and teardown, but the stuff in the middle often looks identical, which is really great for the usual software development reasons. Plus, they also give you some window functions. So if I want to compute like moving averages or something over these windows, those are easy to do as well. Okay, so I'm going to go through a little more detail about the inverted index implemented in Spark, and this time I'm going to count, like I said I would. So let's walk through this, and I hope you can read it okay. Well, it's typical Scala, so we start off with some imports, and then I'm going to use a singleton object to do this and just write a main routine as we normally would. You always start with a Spark context, which is your entry point. It knows about where the master is. That's actually the first argument. I'm telling it where the master is located in the cluster. The second argument is just a name. And it also gives me hooks for reading files and that kind of stuff. In fact, I'm going to use that next. I'm just going to load some text data, and let's imagine my web crawlers have already staged that data, so now I'm just reading it in. And then I'm going to do this giant expression where I'm going to walk through a sequence of transformation steps to go from point A to point B, which is the answer I want. So let's assume that this data coming in is actually just raw text, and it's tab delimited, so that URL is the first thing, then tab, then whatever is left is the document. So that's all I'm doing is standard line split. Give me the first two elements split on the first tab, and then I'm going to return a tuple that's the 0th element and the first element in the array. Again, that'll be the document ID and the contents of the document. So that's how I process the data initially. Here's my flat map again, very similar to the one we saw for Scalding, where I'm going to split on everything that isn't an alphanumeric character, which is terrible. I mean, I really ought to use string tokenize here, but for the sake of argument, it's good. And then I'm going to put out that same key value pair we saw for Scalding, which will be the word and then the document ID, or in this case, the path to the document is what I'm calling it. So now I have this two-element schema. They're both strings, but at least in this example, one is a word and one is a document path. This is the classic idiom for counting, where I'm going to basically create a new tuple where I'll use as a key the nested word and path pair, and then a seed count of 1 for each of those tuples. And then there's an optimized version of group by. I could do group by here actually to get all the words together, but then I'd build up these big in-memory data structures, and all I really want is the size of that big in-memory data structure. So the convenience for optimizing is this reduce by key, we're able to basically do a group by over all those word path pairs and then apply this function to the rest of the tuple, which is just those integers, and that's what does the counting. So the output of reduced by key, I think, do I have a, yes, actually I have a little example of that. So it looks something like this: a unique word path pair and then some count greater than or equal to 1 is what would be coming out of this. So actually the number of records will have dropped dramatically at this point. This next line I absolutely love, because if I had to write this in Java, it'd be another 20 or 30 or 50 or 100 lines. But basically, notice all I'm doing is I'm moving parentheses in this line. And that to me is like the ultimate in being a lazy programmer and getting stuff done fast. And why am I doing this? Well, I still have this word path key, but now I want to get to the point where I have just words as my keys, because I'm building up the inverted index. So all I did is just shift the parentheses over, 1 comma. And, incredibly concise code that would be nasty, nasty, nasty to write in Java. And probably I would screw it up the first time. So this, just to be clear, this is what I had and this is what I've got now. I just shifted parentheses. So now I want to actually do a group by over the word, which is the first element by default is always the key in these tuples. So that builds up, groups with just, all occurrences of Hadoop, all the occurrences of HBase, and so forth. And then the last step is and that's what that looks like. It's that you actually get a sequence with all of those combinations there. And then lastly, I'm just going to format the output. That's all this stage is really doing. Map values is a way of just saying, I'm not going to modify the key. I just want to work with the values so I don't have to pattern match on the key that I'm not changing. So basically, Spark code looks just like Scala collection code, except for a bunch of optimized things for big data applications like group by key and map values and things like that. And then finally, I'll just save the results. So something like this is what's coming out now. And I'll save the results. I forgot to change. ArgZ was just a little hack. I took this from a tutorial I've written, and that's just the path where I'm going to write the data. And when I'm done, I'll stop it. Here it is again, the whole thing. It's now 14-point font, so I think maybe a third of you can read this, ignoring the light. All right, so why is this great? Well, we have this incredible DSL at our hands, to work with. Just beautiful combinators. Look at the red here. You guys know these things. They are just, really carrying a lot of power with very little effort on my part. I'm just sequencing these things together. All I'm doing is thinking in my mind, all right, I'm here, I need to get here, but first I've got to do this. I know exactly how to do that. I'll do a reduce or a map or whatever. And that to me is just so beautiful. I just love looking at this code. The only thing I could think of that could possibly make it more concise is if I could somehow get rid of the case keyword. But I need those for pattern matching, so I really can't make this any more concise. This reminds me of another DSL I loved in college. Who knows what these are? So, Maxwell Equations. These are the equations that unify electricity and magnetism. I used to have a T-shirt with these on them. Actually, it was this color, as a matter of fact, now that I think about it. But I just love this because I can look at this and I know exactly how they're unified and how they're different. Like there's actually a charge density for electricity, but there isn't for magnetism, at least that we know of. We keep looking. There's a tremendous amount of information hidden behind this. So my phone's in my other pocket. The phones that you're using, the only reason they work is because of these equations and so forth. So I love DSLs when they're done well. But wait, there's more. We've got more we can talk about. And I have a few minutes to do it, I guess. Well, one of the reasons this is all succeeding, one of the reasons Scala is the great language for this, is because of the JVM and the ecosystem that's built around it. Just including all the old tools we've been using and some new tools. We'll actually come back and talk about a few of these in a few minutes. And even Clojure. It could have been that Clojure would have won this battle, but they didn't really go after the community in the same way that the Scala community did. And also, I think it's a true statement that Scala is an easier step for a Java developer to make, to go to versus Clojure. So that's the other factor. There's now a rich ecosystem of big data tools, many of which started out as Hadoop tools and now are migrating to be more general purpose. That's the Summingbird icon. So we talked about the first three. what we're finding when we talk to customers is that these three are really popular right now. Spark, Apache, Kafka, and Cassandra are like the new troika of big data, if you will. And then there's other things that you may know here as well. Well, to be fair, it's not so much that Scala is fantastic, it's that functional programming is fantastic, and Scala is based on functional programming. At the end of the day, every program we've ever written is read data in, apply mathematics to it, and write data out. It doesn't matter what UI we slap on it, it doesn't matter what kind of object model we build. We're always just doing mathematics on data. And nothing makes that more evident than big data itself, where we are honestly doing what we've always been doing, which is manipulating numbers, strings, etc. So functional programming is such a perfect fit for this that I actually believe that big data is the killer app for functional programming. More so than the concerns about writing concurrent code, which was originally what got people interested, including me, in functional programming. I really think it's mathematics in the practical world of big data. So let's talk a little bit about mathematics in Scala. There's two libraries I want to talk about. One is another Twitter library called Algebird. And I want to talk about a trivial example, at least it seems trivial on the surface, which is addition. Now, if I'm bringing back horrible memories of 6th grade, I apologize, but we have to get through it. So what are the properties of addition? Well, we start with a set of elements. Say, for example, the non-negative integers. There's an associative binary operation, and all that fancy stuff means, if you don't remember, is that if I can add A and B together first and then add C, and that's equivalent to adding B and C together first and then adding A. Now, why is that interesting? Well, so imagine I was doing thousands of these, or maybe a billion of them. I could actually do them in pairs and do it in log n. You know, just if I had enough cores to do this in parallel, I could do some of these additions and then add them together, and it wouldn't matter how the system scheduled which got added together first. They would all end up with the same result. So this associativity is crucial. And then finally, there's an identity element. So A plus 0 is equal to 0 plus A equals A. Anybody confused at this point? Hopefully not. Well, why is this interesting? It turns out, getting back to category theory, there's this thing called a monoid. It's actually just a generalization of this, and the rules are all the same. I have some set of elements, I haven't said what they are yet. I have some notion of a binary operator that's associative, and then I have to have some notion of a zero. And technically a semigroup would be I don't have the zero, but we won't go there. All right, so why is addition interesting? It turns out almost everything that people like Twitter care about, like what are the top occurring tweets right now, or the top hashtags, who's got the most followers, you know, what's the distance between this guy and this guy, all of them can be generalized as monoids. So if I have an infrastructure that only understands monoids, and then I have an implementation of top k, you know, for some integer k, or averages or whatever, that's implemented as a monoid, then I can just plug that right in and just do my calculation, and once again I'm back to writing scripts. I don't have any real work to do. Well, you can do trivial implementations of these that will break down quickly at Twitter scale if you did the naive thing, because of the amount of memory it would take to implement. Not all of them, but some of them. But what if you don't actually care about 100% accuracy? What if you're willing to tolerate some error, but in trade-off, you want to be able to use much less space, much less memory. And you want to be able to tune that choice. Well, it turns out a lot of these algorithms have approximations. And here's some of the names. Hyperlog will give you an approximate answer for how many elements are in this set. Minhash you can use to compare sets. Like, you know, how close is this Twitter graph to that Twitter graph? Bloom filter, you know, does this element actually belong to a set? And I'll give you an example of this. This is an old one that's been used a lot. If I have a giant database and I'm looking for a record by a key, but I'm using a Bloom filter to tell me, all right, is this key actually in these files? The Bloom filter will tell me approximately that whether or not it is actually present in the file. So in other words, if it says it's not, I don't have to look in the file. So it's a way of skipping part of my search and narrowing down the search space. Specifically, Bloomfilter will occasionally give you false positives, but it'll never give you false negatives. So I might do some wasteful searching, but I won't search everything, and that's the key. So they have a mantra, if you will, at Twitter, which is to hash. All these things are actually based on computing hashes. So hash your data rather than sample it and effectively throw away some of it. Hash, get approximate answers, but work with all of the data. If you're interested in this topic, I highly recommend looking at this presentation that Avi Bryant, who was at Twitter a few years ago. If you just Google add all the things, you'll find it. But he goes into great detail about why all this works and how they've exploited monoids. So I would say that maybe after monad, and there I use that word, I would say that probably monoid is the most interesting category in programming, at least especially in big data. All right, the last one I'll talk about is Spire, which really takes me back to my roots in physics, which is numerical computing, like avoiding round-off errors and doing things fast. So there is some overlap between Spire and Algebird, but they really are focused on different things. So if you work with complex numbers or accurate representations of real numbers, you'll be interested in this. It has all of the standard algebra types like monoids, and I mentioned semigroups and so forth, trigonometric functions and so forth. But you know what? There is one other thing I really want to talk about that's also functional, and that's our old friend SQL. So we all went through this fad of believing that SQL was dead and NoSQL was the future, and hey, I can write everything as JSON. That sort of thing. But actually it turns out that SQL is not only really useful, it fits very beautifully with this idea that everything should be functional. And just as an example, I might have a table, let's say this is the output of the inverted index, but I'm just going to keep the top 2 results for each word, and I'll just use integers for my document IDs and so forth. So that's all that is. I can represent this as a stream in Scala or as a database table. That's kind of not terribly interesting. But basically a lot of the same operations I would write in SQL, I can write in Scala as well, or Spark or whatever. I can do a where clause to say, just give me the records that match these criteria. I can say, just give me these columns out of my data set. And it's funny, when you get to things like joins and group bys and order by, it's really hard to beat the SQL for a very concise code, as great as Scala is at this. But I can do things like order by and group by too. So to finish, can we unify this picture? Can we do something that actually gives us, I guess I have to hit the button, gives us the core of Spark like we already saw, lets us embed SQL queries when that's the most convenient way to express what we want to express, and do this on the fly with streaming data. And you know what the answer is going to be, it's yes. And it really reflects the fact that Spark has really good ideas about primitives that it's exposing and efficiency. So I have a mocked up example taken from a Spark workshop that I wrote, available from TypeSafe for a very reasonable price, I might add. And what I'm going to simulate is I've got airline data coming in. So as flights take off and land at airports, I'm going to count how frequently a carrier flies between 2 airports. So I'll just use some of the data that you can actually get this data set online for free. It's actually kind of fun to play with. And it's actually shocking how many flights are canceled when you look at this data set. But anyway, so I'm going to just keep track of the flight number, its carrier, and the origin and destination airports. And a trick I like to use sometimes is, and this is quite common in Spark, is to use a case class to represent the schema of this data set. And then what I like to do is create like a parse object. If I'm going to be parsing raw strings, I'll do that to parse each string that comes in and convert it into one of these objects. And I'm using an option because I can't return like a validation error. I just have to keep going if something doesn't parse. So somewhere in here I'm going to handle bad records and just return none, but otherwise I'll return a sum wrapping this. I'll need to connect to some Spark server somewhere. I'm going to listen on a socket, at a port and server address. We're going to create a Spark context like we did before at some master, and this would probably be a real cluster, not just running locally. I'm going to call it much.Wow for whatever reason. And the other thing you do is when you want to use streaming or SQL, you just wrap that Spark context in another context object that brings in these extra features. So that's what I'm doing here. When you do streaming, they call it a discretized stream because each of those time intervals I mentioned is going to get stuffed into Spark's regular data structure for sharding your data over the cluster. But they use discretized to mean that it'll be discrete chunks. So I'm going to listen to a socket that's just writing text, regular strings to me. After every iteration, this next bit of code will be called to parse the lines in that text to give me my schema, which will be the flight type that I showed you earlier. And then RDD is the name of that distributed data set. I'm kind of skipping over some of these details, but nevertheless, here's where the SQL comes in. On each iteration, I can register that RDD as a table, temporary table, like I might do in Hive or some other tool, and then I can write a SQL query. And this is the query that's basically doing a group by over the carrier and the airports, and then counting how many flights were there between two pairs of airports, and then ordering them by the most frequent pairs. So kind of a trivial calculation, but it nonetheless, it very concisely shows this example of mixing SQL, when that makes sense, into your program. And then once I've set all this up, I start it running. This has all been lazily evaluated until I said go, and then I'll just wait forever, probably, for it to stop. Okay, so to wrap up, I think it's fair to say basically that Scala has actually won. We are, in fact, dominating the big data space now. There's still a lot of Java people, of course, and data scientists are still using Python and so forth. But we're seeing a big uptake in Scala because it's such a great fit for this. It gives us the flexibility we need. And with that, I'll say thank you very much.